Hello everyone. I'm back with another LeetCode problem called merge k sorted list. So this is tagged as a hard problem in LeetCode, but it's not actually that much hard if you know exact way or which data structure exactly to use. So let's go through the problem statement once. So it says merge k sorted linked list and return as one sorted list, analyze and describe its time complexity and or complexities. So what does it exactly mean? Like if given a list of list nodes, like these are linked lists, and the input will be a list of linked lists. So 145, 134, 26. You can see all of them are in sorted order, so we have to return by merging all of them and make one single linked list and return the head pointer, or rather head node of the resultant linked list. So from this input we can see that if we merge all of them, then we will get 1, 1, 2, 3, 4, 4, 5, 6. So we have to do this, and let's see how we can do it. So now, as you can see, this is the input given. So as I have said already that this each input is a single linked list. Like this one is a single linked list, this one is a single linked list, and this one is also a single linked list. So the question is called merge k sorted list. So for this problem, for this particular example, the k is 3, like 1, 2, 3. So we have to merge these three lists and make one single list which will be also in sorted order. So as we can see here, this first list is in sorted order, like 1, 4, 5. It's increasing. The second one is also in sorted order, 1, 3, 4, and the third one is also in sorted order, 2 and 6. So what are the ways we can actually solve this problem? Let's suppose we have three lists for the time being, and we have to make a resultant list which will contain all the elements. So uh, it is a common sense that how many elements will the resultant list will have, like the total number of elements these three lists have, like 1, 2, 3, 4, 5, 6, 7, 8. So the resultant list will also have 8 elements. So first of all, how to check that which element is smallest of them all? Like first we check in this list which is the smallest element, obviously the first element. In this the first element, in this also the first element. So amongst the all the three first elements, which one is smaller? Either this one or this one. So we can take any of them. So we'll take one. So I'm just first explaining the brute force approach, then we will move on to the better approach or which data structure to use and all the complexities and all. So okay, so we have taken one. So then after that, the pointer from here, first of all, I forgot to mention something, that we will be pointing to the first elements of all the list. So we were here and we calculated the minimum elements, and we seen that this element is smallest, and so we have taken this in the resultant list and moved the pointer to the next element. So now which one is the smallest among these three? Now this one. So we have taken this and put it in the resultant list and move the pointer to the next, move the pointer here. So now again amongst these three, which one is the smallest? This one, 2. So move it to the result, move the pointer to the next one. Which one is the smallest? 3. Move it here, move the pointer to the next one. Which one is the smallest? Either this or this. We will take this one. So move the pointer here and take the 4 to the resultant. Okay. Now again, which one is the smaller? This one. So move the pointer outside the list. That means what? We have completely traversed this list. So all the elements from this list is already taken. So again, we take 4. Okay. So now only two elements are left. Which one is smaller? 5 is smaller. So 5 is taken. The pointer moves outside the list. That means this list is already traversed. So 5. And now only one element remains, 6. So 6. So as we can see here, we had here we had 8 elements, and in the resultant single list we also had 8 elements, and they are in sorted order. So this is the brute force way we can just traverse through all the list and check for each element. So this is not a very what we'll say, like efficient solution, or not a very good way of solving this particular problem. So you will obviously get into trouble, like when the k value is like more than 3, like if k is 10, like 10 list is given. So it's not a good approach to solve it this way. So now what we will use is a binary heap to solve this problem.
So now let's look at the binary heap approach. So as I said, we will be using a binary heap. So let me give you a brief introduction about what heap is and how the heap data structure actually works. So a heap kind of look like this. A heap, you can basically call it a complete binary tree where it will maintain a particular property. What that property is, like for the main heap which we are going to use in this particular case, the top element will always be minimum. Like all the elements for each subtree, the I mean child elements will be less than the value of the root element. Like for example of this tree, all the child elements will be greater than the root element for min heap. And if it's a max heap, then the top element will be maximum and all the rest of the child elements will be less than that. So this is the basic heap structure. You can go to Google and search for the theoretical part of heap. So I'm not getting very deep into heap, so we will be just using heap data structure to solve this problem. So this is the concept of also heap sort. So what we're going to do is take each list and put all the elements to the main heap. So like first we go to this list and traverse through it and put all the elements in the main heap. So what will it look like 1, 4 and 5. Then we will go to this heap and put all the elements in the heap again. 1, 3, 4. Lastly 2 and 6. 2 and 6. So this is a kind of a broader approach, or like a higher level view of heap. If we convert this into actual tree formation or actual heap formation, then it will look like something like this. So I haven't actually written the exact numbers over here, but you can do it also like this. We don't need it for this exact example, so we're going to stick with this one. We just need to understand the concept of it. So after that, if we are going to pop or take out one element from the top, one property of heap is you can only take out element from the top, like from the root element. So for this example, you can only take this element out, else other elements cannot be taken out. So uh, if this element is taken out, then the whole heap will also rearrange itself and also make it in such a way so that it maintains the property for min heap. Like the minimum element will be again in the root, so it will balance itself again. So that's a different, I am just getting out of the topic here, so this is a theory part. So for the time being, let's concentrate here. So first, if we take out the element, or rather pop the heap, which element will become come out? The minimum element. So minimum element will be 1, so 1 will come out. So let's take 1 out. Then again we pop, so again the minimum element 1 will come out. We will store it here. Again 2 will come out, minimum element. Every time we pop, the minimum element will come out. So every time we pop from here, we store it here, pop from here, store it here. So as you can see, after each pop element, it will be automatically extracting the minimum element, so it will be in the sorted order. So this is why the heap data structure is very useful for this sort of operations. So now coming to the time complexity. So what will be the time complexity for this operation? For inserting, the time complexity in heap is log n, and for each element and traversing each element in this list, it will be n. So the total time complexity for this particular approach will be order of n log n. So this is a better approach, and this is quite efficient and easier also, rather than the previous approach, which were like comparing all the minimum elements and finding the minimum amongst all the minimum elements. So this is a better approach. So let's just implement this.
So now, without making the video much more longer, so I have already written the code over here. So let me just walk through it. So first of all, we are going to use a main heap. So for that, Python has a module called heapq. So we will import it first of all, heapq as HQ. So if you are from Java background or C++ background, in Java, as I actually know, there is a collection framework class called priority queue. You can also use priority queue as a heap, and also there is one I think in C++ STL also. So I'm in the Python domain, so that's why I'm using heapq module. So first of all, I have to import heapq as HQ. Then how this heapq model, or how this heapq module actually works is, it takes a list or empty list and heapifies it. So what this heapify function actually do is, as I have mentioned, that it will make a list into a heap. So such a way that all the properties a heap should actually obtain, uh, the list will be also converted in that way. So this heapify function will convert the heap list as actual heap. So that's why we are written heapify. So now this nested loop, what this nested loop will do is take each element and put it in the heap, take the next element again and put it in the heap. This way we using two loops traversing through all the elements and putting them in the heap. Now we have to return the head node of the newly created list. So that's why we are creating a new list node head and storing some random value or like -1 in it, so that it doesn't interfere with the actual values. So we are making the new head list and storing -1 in it. Then we are making a pointer current which will be pointing to the head node. Then we will traverse the whole heap until try to traverse the whole heap and like pop out each element from the heap until the heap is empty. So that's why we have written until, or while the length of heap not is equal to 0, we will take out each element from heap, which will be done using this heap pop method in Python, and store it in a variable, and then using that variable we will make a new node, and the current dot next will point to the next. It's just like simple linked list insertion. You can clearly understand it. So after that, current will be current dot next. Like we are just traversing the linked list. So this is basic stuff like inserting into a linked list. And after that, we are returning head dot next. So what is why it is head dot next instead of head? Because we have just created one arbitrary head pointer because we didn't have any head pointer, so we have to create one. So the arbitrary pointer we don't want. So from head dot next we are having the desired output, so that's why we are returning head dot next. So this is the code, so let's submit it. Why it's submitting, let me tell you one thing, like don't focus on this part. This is just basic linked list stuff. You can understand it clearly if you just spend 2 to 3 hours. You can completely understand linked list. So the main concept or main difficult part, the reason behind that this problem is tagged as hard is because we or many of us don't know which data structure exactly to use for this sort of problem. So this part should be clear after watching this video, because we are using a main heap and heap queue module in Python. So yeah, so that was how you can solve the merge k sorted list. Thank you for watching and see you in the next one. Goodbye.